See, the working envelope is pretty tiny, but it can be very fast. Why is it fast? Well, to begin with, they are very lightweight. These parallel manipulators, and it says parallel because you got multiple actuators moving the same thing. So that's kind of parallel. So if this is the base, this is the end effector, you got multiple actuators moving the same point. This is called parallel robots or parallel manipulators. When you have the base have multiple joints in series, this is called serial manipulators. Okay? So this Delta robot falls into the category of parallel linkages. Okay? The strength of this is you got, basically you don't have any motor at the end of your, at the end effector. Okay? You notice that in the, like the Fanuc or the KUKA robot arms, the base is much bigger and it gets smaller as you get to the end, right? Which kind of makes sense. And think about your body. I mean, you have bigger muscles here, smaller muscles as you get to the end, right? Why?
Inertia.
Inertia of what?
Moving.
You have also got inertia here. Why is the inertia bigger here? Is what you're trying to say, right? The inertia is bigger. Why? In this case, what are you moving? Not just the arm.
It's heavy.
Why is it heavy?
There's a motor in it.
There is motors at the end, at each joint that you're moving. So in the serial manipulators, the end is a tiny motor, but the base is responsible to move everyone, right? Including the motors at the elbow, at the wrist, and everywhere else. So it's like these acrobatic moves where the guy on the bottom, and then you got multiple people climbing on top of each other. Like the guy at the bottom sustains the weight of everyone, and the tiniest guy or gal climbs and be at the top, right? So people like you would not be at the top. You're gonna crush everyone. So serial manipulators tend to be slower because big inertia. You're moving everything. Here, the end effector has no motor, right? It doesn't have a motor. The motor is all on the base. So that's why you can do very fast movement. Let's look at some of these in action. So 135 parts per minute. 135 parts per minute. So we're talking about like 2 parts per second. This one has a revolute joint at the top, not a parallel joint, not a prismatic joint, right? Pretty fast. Many of these arms are made from carbon fiber too, reduced weight, composites. Yeah, so tiny working envelope, but very fast. Many times it's combined with a vision system because you need to know where it goes. Vacuum comes at the end. Okay, so let's take a quick break before we get to the second subject, which is motors. I forgot to give you a pre-test and a post-test. Yeah, 10 minutes is fine.
So it's like, was it hydraulics, yeah, hydraulics last time, where we meet like. Okay, so why we have this, or why we have this.
My question is, how is it cable? One to make like the logic type cable. I know probably like logic, but I don't understand like how. Because I saw graduation. Because I saw graduation, I was like, oh. Yeah, no, it's there. Hold on, no, assignment not to right?
No, assignment to
It's in PDF.
Sumpah. Make the logical sequence operation.
I don't understand.
So,
That's confusing part. I don't understand why.
maybe it's related to the sensor.
Maybe, but the thing is, I don't really understand that part. The sensor, like.
Maybe it's the S part because I don't think it's a logic table.
I don't know.
Yeah.
Are we at week 5?
6.
But we skipped one class, right?
Yes, a week 5.
Okay, I post a link. Check it out. Pre-test and post-test. Linear and robotic actuators. Why don't you do that? And then we'll do another test at the end. Okay, I forgot to do this pre-test. It's under week 5 material. Group 2 of classroom. Go ahead and do the pretest in Google Classroom. Okay. Did the pre-test already?
What?
The pre-test in Google Classroom.
Iya, tadi kan buka.
Okay, go ahead and do it if you haven't. And let's keep moving forward on choosing motors.
Dikasih Pak.
Yeah.
Oh.
Okay. Content. Getting the correct motor for your application is very important, so I'm going to show you the 5 key steps to achieving this. First, we need to know the type of application. These fall into 2 main load characteristic categories. First is constant torque. such as conveyors or extruders, which run at relatively steady levels of power. Second is variable torque, such as centrifugal pumps and fans, which have a varying power load, with the highest torque typically occurring at the highest speed. The second step, understanding the power requirement. If this is not known, we use this formula to calculate it. The third consideration is required to start up inertia, along with the number of starts per hour. The life of commercial airplanes is measured by their number of landings. In the same way, the life of a motor is proportional to the number of starts it makes. The fourth step is the consideration of the duty cycle, S1 continuous or intermittent running. Our last consideration is motor hypoxia. If your motor is going to operate at altitudes, it must be derated on a sliding scale using this formula. Or you could remove all the risk. Call or email us and we will size the motor for you. When you buy your ABB motors from Quantum,
Alright, let's just okay. Let's go into this. This goes into more detail.
Welcome back. Joe.
And I'm Janet.
With Grow Shop. In this fourth video in our series, How to Choose an Electric Motor, we'll begin discussing our 4 motor types: universal, permanent magnet DC, AC induction, and brushless DC.
So these are the big categories, okay? Of course, there are still slight variations, and even you can argue a little bit of an overlap between these. So you got universal, DC with brush, AC, induction, and BLDC, which is brushless DC. First, let's look at the universal.
Throughout these videos, we'll go over their construction, characteristics, advantages and disadvantages, as well as teach you how to interpret the motor performance curves for speed, torque, and efficiency. There will be trade-offs between the different motor types, and sometimes the best choice isn't obvious. That's why we'll give you some aids to help you understand the pros and cons to make the selection process easier. Janet, do you want to start us off on universal motors?
Sure, Joe. Universal motors are great for AC or DC applications that need a simple, high-speed, low-cost motor with intermittent duty cycles. They're durable and suited for rough, high-vibration applications where low noise is not needed, such as commercial concrete drills or floor sanders. As you can see, we have the basic components of a universal motor laid out here. Both the armature and the field in this type of motor are wound with magnet wire, and the electrical connection to the armature is made through the commutator and brushes.
Okay, so we will not go into the construction of universal motor. Have you guys learned this in electric drive? Yes? No? Okay, so but the focus of this course is on the applications of these motors. So we'll focus on selection, okay? But nevertheless, it doesn't have any permanent magnet. Both are actuated. The magnetic fields are created with coils, both the stator and the rotor. And it does have brush. Universal motor is ubiquitous, like it's everywhere. Think of anything cheap that has a motor on it. It has a universal motor, okay? Because it's just cheap. It spins high speed. You don't need any accuracy. Something that you just need to spin. Think of the applications. Give me the applications. Drills.
Grinders. Things that don't need to run all the time. Blenders.
Blenders.
Garage doors.
Garage doors.
Garage doors, yeah, sure. Fan.
Portable
I don't care if it rotates at 1,000 RPM or 1,100, right? Who cares? It just spins, yep.
Those like portable air compressors.
Oh, the tire pumps.
Yeah.
Yep. Yep. A lot of them are also DC though. But yeah, you can do a universal motor of that.
But I guess usually they don't run all the time, right? Because it's
Yeah.
not really all that reliable.
like a fan, you probably want like something brushless.
Right. For really long life, you don't want to brush because these will be the first to go. Okay? They are friction. They cause friction, and so these are basically carbon sticks, like a pencil. Carbon conducts electricity. Just in case you don't know, it's a very good conductor actually. In Indonesia, they usually call it arang. Okay, so if your motor goes out and they're trying to rebuild it, and they say, oh ini arangnya habis. Nah itu artinya that means the carbon brush. It's not a brush, but it's just a solid rectangular piece made out of like pencil. Okay.
It's slip ring, right?
It is low friction, but it's still friction, and it conducts electricity. So it allows just sliding contact, sliding electrical contact. That's what it is. These plates can also wear out, but usually the copper plates here will wear out after a few carbon replacement. If you buy like an angle grinder, they usually come with a set of extra brush. Okay? They call it a brush because it kind of slips and brush through it, through the copper plates, the commutator. Okay? So this is the first thing you replace after X number of hours.
There are two characteristics that set the universal motor apart from most other motor types. First, it runs off both AC and DC power, giving it the name universal motor. Second, a universal motor is capable of running at extremely high speeds, from 8,000 to more than 20,000 RPM. These two characteristics make the universal motor fairly unique and ideally suited to specialized applications. Several other characteristics of the universal motor to consider are the high starting torque, the 55 to 70% efficiency rate, and the average life expectancy of 500 to 2,000 hours.
So it's not that efficient, not the most efficient motor, but it works.
One main advantage of the universal motor is its high power density. It's not uncommon for a universal motor to have over twice the continuous output power as an equally sized AC motor. Additionally, its low cost, portability, and ability to run without a control make it worth looking at. A few downsides to universal motors are that they are noisy, inefficient at low voltages, burn out quickly in stall conditions, require high maintenance due to the brushes and the open frame design.
Where do you think the noise comes from?
Brush.
The brush. And there are sparks on that brush too. So, I mean, if you're working in hazardous or flammable conditions, that's also not desirable.
But Honda uses brush motors on their fuel pumps on the motorcycles.
Really?
They break.
They also have poor speed regulation, and the high speeds prevent gearbox usage.
That's right, Janet. Before we look at universal motor performance curves, I'd like to quickly comment on low voltage and universal motors. If you operate a universal motor under 100 volts, the efficiency drops drastically. With a battery input source, the universal motor could quickly drain. As a rule, other motor options should be considered for low voltage situations.
Here we have the typical speed torque curve of the universal motor. This is the cold motor curve, and you can see that it's fairly linear with good starting torque. The sharp upward curve as the torque decreases is a unique characteristic of the universal motor. Now, we've added the hot motor curve. Here you can see the effect that heat has on motor performance. For a given torque point, the motor will run a little slower as it heats up. All right, now...
Okay, so a typical torque curve of universal motor, it's similar to a DC motor. Besides, it does work on DC. So this is the torque, this is the RPM. So at maximum RPM, zero torque, this is called the free spinning RPM. And at maximum torque, it's at 0 RPM, this is called the stall torque. Okay, when you look up a spec sheet, oftentimes it gives you the stall torque and they give you the no load RPM. They give you these two. But a good spec sheet will give you also the rated torque and the rated RPM, which is kind of what is designed to do continuously.
We've added the motor's efficiency curve, the black dashed line. Under ideal circumstances, the motor's peak efficiency will occur very near the motor's operating torque. However, in most cases, the actual peak efficiency will occur at higher torque than the rated torque.
So this zone will be ideal, which is kind of a pretty high RPM and a pretty low torque. Okay, so for a universal motor, you want to aim for that.
Janet, I'd like to make a comment about speed torque curves. On our website, you'll find that our motors have speed torque curves associated with them. This allows you to see exactly how any given grow shop motor will perform. Up next in our series on how to choose an electric motor, we'll look at permanent magnet DC motors. For more information about grow shop or any of our universal motor products, check out our website at www.
Okay, so let's look at the next one.
Series How to Choose an Electric Motor. We're discussing our 4 motor types. Previously, we looked at universal motors. Now we'll be diving into permanent magnet DC motors. DC motors are one of the most well-known motor types. They're ideal for low-power applications and those needing high starting torque, and are often seen in the automotive and agriculture industries.
So for smaller appliances, smaller drills, you will see these DC motors. Okay, I think hand drills are mostly DC motors.
A DC motor consists of a wound armature, a commutator, with brushes that interact with the magnets in the housing. DC motors typically have a totally enclosed construction. They have a straight speed torque curve with high starting torque and low no-load speeds. They can run on DC power or AC line voltage with a rectifier. Operating speeds of 1,000 to 5,000 RPM.
So slightly lower RPM, lower voltage.
And enclosed construction make DC motors suitable to use with gear reducers. DC motors have the second best efficiency rating of our 4 motor types at 60 to 75%. The brushes must be inspected regularly and changed every 2,000 hours to maximize the life of the motor. There are 3 main advantages to a DC motor. 1, it works well with gearboxes. 2, it operates on DC power without a control. But if speed regulation is needed, a control can be used and is inexpensive when compared with other control types.
How do you control?
Third.
How do you control a DC motor speed? PWM stands for pulse width modulation. What does it basically do? What does it basically do?
On and off.
You go on and off real fast, right? And how long you're on versus how long you're off is it's called the duty cycle of the PWM. So it goes from 0 to 100. 100 meaning like full on. And that's cheap to do. PWM is cheap to do. Just use a transistor, MOSFET, and you're ready to go. AC motors, as we shall see later on, is much more complex to control. You control the frequency.
Most DC motors are a great option for a price-conscious application. Drawbacks to consider with a DC motor are the brushes, because they are high maintenance and can create some noise. Cogging can occur at speeds of less than 300 RPM, and there's potential for significant power loss on full-wave rectified voltage. If you're using a gear motor, be cautioned that the high starting torque can damage the reducer.
Now we'll look at the typical speed torque curve of the DC motor. You can see the linear curve we spoke of earlier. If you look closely at the hot motor curve, you'll see an interesting phenomenon. As the motor temperature is elevated, the no-load speed is increased. This is due to the effect that heat has on the magnets. As the motor cools down, the speed will return to normal. Note the other end of the curve where stall torque is reduced for a hot motor. Here we've added the black dashed efficiency curve. Under ideal circumstances, the motor's peak efficiency will occur near the motor's operating torque.
Stay with us as we continue our series, How to...
Will occur
So here's a DC motor. It looks similar to a universal motor, but notice the much lower RPM range. Also have a good starting torque. Starting meaning from 0 RPM. It actually has a maximum torque. By the way, which is what's fun about EVs, is the instant torque, like from 0. You don't need any torque converter, you don't need any clutches. Just press the pedal. In fact, you will feel the best acceleration at 0. Not much higher in the near the red line, unlike combustion engines. So, but you're most efficient here, though. So you want to operate like 80% of the no-load speed. This is also ubiquitous. It's like everywhere. The DC motor. It has a permanent magnet. Tends to be bigger. Big DC motors tends to be expensive. So usually when you start to need high power, you go to universal motor or AC induction. Okay, let's move on to the third type. Let's talk about AC motors.
And I'm Janet.
With Grosha. We're back with the 6th installment in our video series, How to Choose an Electric Motor. In this video, we're discussing AC induction motors. AC motors are one of the most common types of motors used in a variety of applications because they run off the AC voltage found in wall outlets.
The typical construction of an AC induction motor has a wound stator with a rotor consisting of laminations and cast aluminum and a shaft. The stator winding determines most of the performance characteristics of the motor. AC and DC motor commutation are similar. However, the winding of an AC motor takes advantage of the alternating AC power to do the commutation without requiring brushes. The field is created by the currents induced in the rotor. Think of it like an inside-out DC motor. An AC motor, depending on its winding, is built to run off either single-phase or three-phase AC input power.
So an AC motor, think of it like the magnet is in the middle, like in the rotating part, the rotor, instead of the stator. But you know, it's not exactly a magnet like with the BLDC.
Can I quickly jump in? There are multiple types of single-phase motors: capacitor start, split phase, permanent split capacitor, and many others. We manufacture permanent split capacitor motors, or PSC. So we will be focusing on these as well as three-phase motors throughout the video.
Thank you for clarifying, Joe. Let's get back to the motor specs. The output speed of the motor is relatively fixed depending on the number of poles with which the stator is wound and the frequency of the input voltage. This is typically limited to 3,400 RPM. Unlike a DC or a universal motor, the value of the input voltage doesn't affect the speed. The primary advantage of an AC motor is the lack of common wear parts, such as brushes and commutators, giving them a long life with low maintenance.
So these induction motors, the way you commutate is not using the carbon brush and the different plates. So you commutate by manipulating the input signal, which makes the controller complex. This is often called the inverter. But it's not just an inverter, it's a controller. Think about it. With servo, then you will also manipulate the position. But these induction motors are very long life. Pretty much the only wear part is the bearing because it floats. There is no touching to the rotating part.
In fact, if properly applied, AC motor life is limited only by the bearings. Other strengths are their ability to maintain speed over a wide range of torque, the low starting current, gearbox compatibility, and speed control compatibility for the three-phase motors. Typically, AC motor efficiency is around 40 to 70%, which is lower than the DC motor. Some weaknesses to consider with the single-phase motors are poor speed regulation and that they require low starting torque for the capacitor to start.
So AC induction is not for a great load. It's good for like a long lifetime. You just rotate at the same speed. You know, conveyor that kind of runs forever. It's a good application.
AC motors in general also have low power levels comparative to size, a lack of portability, and high cost per horsepower when compared to other motor types. Be aware when considering an AC motor that many single-phase PSC motors will actually have less starting torque than their rated torque. This is important because if your application needs to start with a load, a three-phase motor is likely the better choice. There are several reasons to choose a three-phase motor over a single-phase. Three-phase motors have good speed regulation when a control is used and are cheaper than brushless DC motors. They have a higher starting torque than single-phase and have potential for higher or lower speeds than a single-phase when using a control.
Shown here is a typical three-phase AC motor performance curve. This curve is fairly linear and flat until the breakdown torque is reached. After breakdown, the torque drops off sharply and even folds back a bit. In a single-phase PSC motor, the foldback is even more pronounced. As you can see, under ideal circumstances, the motor's peak efficiency, the black dashed line, will be...
Okay, so this is the torque curve. You can see how different it is from a DC motor. Okay? How did the DC motor torque curve looks like? Remember? It's just a line. Right? Maximum torque, 0 RPM. Maximum RPM, 0 torque. Simple. Now, the induction motor is a bit more complex. You got relatively flat torque up to a certain RPM. So that's kind of unique in the AC induction, and so it runs also very smoothly. No carbon brush.
Near the motor's operating torque.
Stay with us as we wrap up our look into our 4 motor types with brushless DC motors.
Okay, so finally, brushless DC is the fanciest of all, actually.
Joe.
With the 10th video of our How to Choose an Electric Motor series. Brushless DC motors, or BLDC, are suitable for a range of applications. Their maintenance-free design and high power density make them a good solution for applications that require variable speed or no maintenance.
Although considered part of the DC motor family, the construction of a BLDC motor is more closely related to AC motors. However, the rotor is constructed of rare earth permanent magnets to produce the field. Their electronic...
We'll hear some noise. Oh, it's from your laptop. The difference with AC or three-phase or single-phase AC is the magnet at the core, at the rotating part. By the way, most EVs use BLDC.
Commutated by a control. They can receive feedback from sensors that determine the rotational location of the rotor, or by measuring voltage in the coils as the motor is operating to determine rotor location.
So BLDC is complex. It's probably the most complex, both in construction and in controls. It needs a Hall effect sensor to detect the position and actually kind of a feedback loop of which field to apply current on. Okay? So the stator is what you control, which field, and then it's like as you rotate the electric field, the motor kind of lags behind and then snap into the position. And so you kind of determine where you want it to go with electrical controls and with the information from the Hall effect sensor. So it is a complex motor. However, it has probably the best of both worlds.
BLDC motors have speed-torque characteristics similar to brush DC motors. However, they require Hall effect sensors and a motor control to commutate. The use of a control makes them suitable for variable speed applications. A BLDC motor takes the advantages from AC, DC, and universal motor types and combines them into one unit. It has the long life, low maintenance, quiet operation, and variable speed ability of an AC motor. The high starting torque and linear speed torque curve of a DC motor, and like both AC and DC motors, it works well with gearboxes. Brushless DC motors have a high power density, second only to the universal motor, and they have the best efficiency rating of 65 to 80%. Despite
Yeah, very efficient, high starting torque, you get everything. you only need to,
You wanna need money.
you need money. That's all, right? Trade-off in life.
Despite these advantages, there is one major weakness: cost. The cost of rare earth magnets and controls drive the initial motor costs higher than a DC motor. But when you weigh the initial cost over the life of the motor and its strengths, brushless DC motors can be worth the investment for some applications.
The speed torque curve for a VLDC motor is very similar to that of a DC motor. This curve represents the motor performance with full voltage applied, but without the control impacting the performance. Since a control is always used with this motor, there is a lot of flexibility with brushless DC motor operating ranges. Take a look at the gold shaded area on the curve. The motor can be operated anywhere within this area. The key to rating a VLDC motor is torque. This particular design is rated at 6.9 inch-pounds of torque, and like all brushless DC motors, the maximum torque rating is independent of speed. The only limitation is that when the speed is lower than 300 RPM, cogging may occur with the motor.
So again, these are the operation area. This is usually the rated torque, and anything below that is fine, which end up with a certain RPM, near the no-load RPM.
The cogging can be lessened by using a more sophisticated control and feedback system. Well, that rounds out our look at our 4 motor types. Let's summarize with a comparison and discuss how to apply this information to your application design process.
As you look at the curves for the different motor types individually, it's difficult to get an accurate comparison. That's why we've created this graph to compare the speed torque curves of all 4 motor types.
So when you lay it all down, look at how they compare in the same plot. Once you put them in the same plot, suddenly you see that universal motors are superior in high speed, right? And you see that brushless DC pretty much covers everything that AC induction or DC can cover with the price. AC induction, you usually operate in the most efficient range that you want, and it's long lifetime with a cheaper price. So if you want long lifetime but cheaper, go with AC induction. If you don't need to vary the speed, vary the torque, you just run an industrial machine constantly, 24 hours a day, go with AC induction.
We're using the same scale to clearly illustrate the differences between the motors. For instance, you can see the dramatically higher no-load speed of a universal motor, the purple curve, and the significantly higher starting torques of DC and brushless DC motors. I'd like to point out that all of these motors are roughly the same physical size, despite their significantly different performance curves. You can download this graph from the link below.
We've also put together this chart to quickly compare motor types and provide a starting point when you have an application in mind.
Okay, so look at this comparison table. I think I have it on the next slide. Okay, so here is the quick reference chart. You see for universal, it's high speed is the specialty, okay? High power, high speed. DC and AC will be kind of a medium to low medium horsepower, lower speed. The efficiency can be up to 80%, depending on your operating range. They are pretty good. VLDC can be the best efficiency though, in general. Lifetime, very high. So I would say that's kind of the biggest reason why we choose AC. Very low maintenance, very quiet, they just spins. Starting torque is the weakness point of AC, but the strength of VLDC and DC. Okay, finally, let's look at servos, which...
This industrial robot needs a drive with particularly high demands.
which a lot of servos are AC servos. There are also DC servos, but they are basically a motor with an encoder.
This industrial robot needs a drive with particularly high demands. Not only does the robot have to be able to accelerate and decelerate fast, also precisely positioning is required. In fact, here's a 3-phase servo motor installed. In this video, we will clarify the term servo motor and servo drive in general, then the 3-phase servo drive. The servo motor is a part of a servo drive, whether brushless DC motor, synchronous, or a robust asynchronous motor. But one thing in common is the detection of the rotor position by a sensor. This can be a resolver or an encoder. In this case, you see an incremental encoder. This sensor device gives feedback.
I don't know whether you can see it, but there are those slits. When the laser goes through, it's a 1, it's blocked, it's 0, and so you get 1s and 0s.
Back to a controller to keep, for example, the rotational speed or torque constant, or to reach the target position as fast as possible. The servo motor system includes the servo motor with its feedback device, a servo amplifier, and a controller. But how do these devices work together? The servo controller sends low voltage control signals for position, speed, or torque to the servo amplifier. Now these commands are amplified up to high power, which the motor can use. The electrical pulses of a sensor are sent back to the amplifier. This amplifier uses this information to control speed and rotor position. The job of the servo motor controller, also named as the motion controller, is to close the loop on the system by constantly interchanging data with the servo amplifier. The motor parameters like torque, speed, or position can be adjusted immediately.
Does that block diagram look familiar? Yeah. Your beloved control technique.
Everything's done.
So you get the controller amplified, drives a motor, which drives a load. However, depending on the changing load and changing environment, the sensor kind of gives you an eye or a measurement whether you need to increase or decrease, or whether you have already achieved the target.
Some manufacturers offer modules, which combine the controller and the amplifier, so you would have fewer parts, fewer connections, and a smaller footprint.
I think most cases it's a module now.
Talking about an AC servo motor, you usually mean a 3-phase synchronous motor whose rotor field is excited by permanent magnets, so you get a very powerful and brushless motor of small size. The stator winding produces a rotating magnetic field, whose rotating speed and force is controlled by the amplifier and controller. In order to position quickly, all these motors must have a low moment of inertia, which can be achieved by an elongated shape. The functioning of a synchronous motor was already explained in another video of our Learn channel. Please check our playlist.
Okay, so that would kind of conclude our discussion on servos. Now, we have already discussed probably pneumatics significantly in the course pneumatic systems, right? So I will go through this just real quickly. It's probably just a refresh of the different pneumatics that you can do.
The compressor generates the energy that powers the system in the form of compressed air.
So any pneumatic systems would need these basic components, right?
To generate compressed air, the compressor draws in atmosphere from its surroundings. It squeezes it or confines it into a smaller space, creating the energy needed to drive the system. Once compressed, the air needs to be dried and cleaned so that harmful particulates such as rust or dirt does not clog up the moving parts in the system.
Okay, so This is the air preparation before it's going to be used. What are these? Why do you need those?
Filter, regulator, and lubrication.
Lubrication. Okay. The lubrication is mostly for the air tools. You hear that sound sometimes in the car shop, whoop, 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 right? Those are the air tools. Basically, you use the pneumatics to spin a fan that spins your drill or impact tool. When you compress out the surrounding air at the same time, what do you get? What happens to the water vapor in the air? It's condensate and becomes water. So the water vapor becomes water. Most of the time it's collected at the compressor tank, but it also condenses up here, and so you want to remove the water as much as possible because it creates corrosion.
The compressed air will travel through a tube or line to the next component, called an air preparation unit, or FRL. FRL is short for filter, regulator, and lubricator, which are common pieces that make up the air preparation unit. Typically, the first unit in the air preparation system is what is called a bulk liquid separator, which circulates or spins the air using specially shaped vanes. The rapid circulation of the pressurized air sheds unwanted moisture due to centrifugal force. The next unit is a filter, which further removes particulate and moisture in a two-stage process. Just like in the bulk liquid separator, a series of vanes or